Now we are going to look at a custom peripheral that we will create, and the idea is to sort of take this up as an example and say if you wanted to create a specific module of your own and you wanted to make it programmable in some way, what are the kinds of things that you would think about, what are the kind of parameters that need to be programmable, what are the kind of status flags that you might want to read back, and how would you implement all of these as part of a register bank. And in order to understand this, we are going to use this example of the smart timer that we are going to build, right. So what exactly is a smart timer? It's a very simple device, right. The name sort of makes it sound fancy, but it's actually just a pulse width modulator. It is similar to the timers that are present, for example, in the ST micro ARM processors, right, and the STM32 timers that can be used for various kinds of PWM applications and so on. This is a much simpler version. Effectively what we are going to do is to create one Verilog module with this interface, right, whose job is just to do pulse width modulation. Now if you look carefully at this interface, you will notice that it has a clock, it has a reset signal, it has a signal to enable the counting, it has two 32-bit values that provide the overall period, the number of clock cycles for which it should be counting before it restarts, and the duty cycle, right. And this period and duty cycle together allow us to say, okay, out of let us say n clock cycles that I have in the system, right. So maybe I have this as the overall period. I might decide that the duty cycle essentially corresponds to maybe 3 of those, right. So period equal to 10, duty equal to 4 would mean a 40% duty cycle. 4 out of the 10 clock cycles, the output which is given by this PWM out over here is going to be high. Now one more thing that we are going to do as part of this particular module when we create it is to say this core will also do one more thing, which is to say that when the period is hit, that is to say when my counter goes all the way up to the period, what should I do? I should go back to 0 and start again, right. And every time that it sort of does this, we call that a wraparound and say that this signal is going to go high for a single clock cycle, right. So we can look at what the code corresponding to something of this sort looks like, and in fact it turns out to be an extremely simple piece of Verilog code. So this is the Verilog code that actually corresponds to the module, the PWM core that we are going to be using, right, and we can actually walk through the entire code and understand it very easily. We have a counter which is going to be once again a 32-bit value, because I know that the maximum value of the period that I can use is going to be 32 bits, right. Now with that what I do is I say that I am going to look for pause edge clock or neg edge reset. If the reset is low, because after all I have used the indicator RSTN to indicate that this is an active low reset. If the reset is low, then I am going to set the count to the value 0 and the wrap also to be the value 0, because it has not wrapped around. Else, in other words, we are not in reset, if the enable signal is low, it immediately brings the count as well as the wrap signals back to 0. In other words, at any point by just taking the enable signal low, I can bring the counter back to the known initial state. Now this is a choice. You might also decide that you want to implement it slightly differently. In particular, you might decide that what you actually want is that when the enable signal goes low, the counter just retains the last value that it had, right. This is up to you. If you want to write the counter that way, then you can do that, as long as you have documented it properly in the design of the in the data sheet that is used to describe your design. In this particular case, I am assuming that when enable goes to 0, the output should become 0. Okay. Else, right, when we have this, what we have is we by default set the value of wrap to be 0, but if the count value equals the period value, that is to say we have hit the value 10 or whatever it is that actually gets us to wrap around, we are going to set the count to 0 and the wrap signal will become equal to 1, right. Else count is equal to become count plus 1. Now the interesting thing if you look at this is the wrap signal will become equal to 1 only at that one instant when count is equal to period, right. Immediately after that in the next clock cycle count is going to be equal to 0, which means that this condition will not be satisfied and this line over here will take over and wrap will be forced back to 0. So the wrap signal in other words is going to be a single cycle pulse, right. So that is just part of how the system is designed. Now we also need to put out the actual PWM output, and what we are going to do over there is once again very simple. If we are in reset, then the PWM output is going to be 0, else we just take the value of count and check whether it is less than the duty cycle, and if it is less than the duty cycle we set the PWM out equal to 1, right, else it is set to 0. So this is a very nice sort of Boolean comparison that we have done here, and it allows us to set PWM out to either 0 or 1 depending on whether the count has gone up to the duty cycle value or not, right. So if your period was set to 100 and the duty cycle was set to 30, then as long as count is less than 30, this PWM out will be equal to 1. The moment count reaches 30 or goes beyond that, PWM out becomes 0. So this is a very simple way of creating a pulse width modulated output, okay. Now what we want to do is, this module by itself has absolutely no software interface, right. The only way to use this would actually be to connect a clock, the reset, the enable signal, check the value of PWM out, set the value of period and duty cycle as 32-bit values directly, right, which means that you could do that if you were wiring it up somewhere, directly connecting it to some other hardware modules inside an FPGA. Yes, this would work fine. What we want though is that we would like to have something whereby I can write a piece of code which allows me to change the period and duty cycle dynamically using some kind of software interface. So for that we are going to take this PWM core and put it inside an AXI peripheral interface. The AXI peripheral interface is going to be very similar to what we have already seen in the previous example of the register bank. Now we will see how we can actually add a little bit more functionality to it. So let us look quickly at the basic functionality that we want from this core as well as the AXI interface, right. The core we have already seen exactly what the logic looks like, and what it does is it basically counts up to a certain period that is specified as an input to the module. It sets the PWM output to be high as long as count is less than the duty value, and it also indicates for one clock cycle if an overflow has occurred. So the functionality of the PWM core, as you can see, is very simple and straightforward. What we want is that we would like to be able, for example, to set the period of the counter through software, set the duty cycle, check whether wraparound has occurred at some point so far. In other words, have I been able to enable it, have I enabled it and has it wrapped around. Also to be able to reset or clear the counter when needed. And one more thing which is missing over here is wraparound will never occur unless the counter is actually enabled and given a chance to run. So I should be able to control whether it is enabled and whether it is counting also from the software interface. So with all of this in mind, we now go and construct a register map, right. And what we say is we have to choose some kind of a base address. What is that base address going to be? Well, let us decide that unlike the case of the ARM UART, which had a 12-bit address space or 4096 addresses, we are going to make do with just an 8-bit address space, 256 addresses. How many registers do we have? 4. Okay. So even if you consider the fact that each register is a 4 consecutive address locations, this is a total of 16 addresses, we have 256. Okay. Like I said, the point is that we are doing this, we are making this choice because it makes it very easy for us to do bit manipulation and alignment of the addresses and even the decoding by just choosing a chunk of addresses out here. I do not want to necessarily restrict this to just 4 because I might want to add some functionality later. At the same time, I definitely do not want to make this something like exactly 7 addresses and say okay, after that I can have something else, because then decoding the base address becomes difficult. I can't just sort of pick out the bottom 8 bits, mask them off and say oh okay, if the upper part matches with something then it corresponds to my peripheral. As you will see, inside the Verilog code that we write, the base address is unknown. This will be known only to the decoder module of the bus interface, right. Alright, so what are the registers that we have decided on? The very first register, and this is a very common convention, register number 0 is used for control. Okay, what kind of control? First thing is we say that this is a read-write register, and within that bit 0 is going to be an enable bit, right. In other words, I can set the value of bit 0 to 1, it will start counting. If I read it back, it will show me that the enable value is 1 and therefore that it is actually counting. Bit 1 on the other hand is a reset signal, right, and this is an interesting kind of signal, as we will see in the logic. It is what is called a W1P, it is a write 1 to pulse. What that means is, if I write 1 into location for bit 1, right, it will set the value of reset, which in turn can be connected to my PWM core. So, the PWM core will see a single cycle of a reset, but if I was to read it back, I will find that the value is still reading back as 0, right. So, it just resets and immediately pulls it out of reset, it does not sort of hold it in reset for a long amount of time. If you want it to remain in reset for a long time, you would use something like this, where I essentially write 1 and then after a while I have to write 0 back into it to disable the reset condition. This is a bit simpler to use. I know that I only want to reset for a single clock cycle. So, what I do is I just basically modify my register bank itself to behave in what is called W1P manner, which means write 1 to pulse. Okay. Now, we also have register at base address 4, which I am going to call the period register. It is also read write, and this is just a 32-bit value, right, which tells you at what point you need to wrap around. At reset, it is set to the value 255, which is 0x0ff, right. Register address 8 corresponds to the duty cycle, read write, it is the threshold for comparison, and at reset it is set to the value 0. Now, what does this mean? What does a terminal count of 255 and a threshold value of 0 mean? You need to go and look inside the PWM core to understand exactly how it is going to behave, but broadly what is going to happen, what should happen over here is, since my PWM out will be set to 1 only when the count is less than the duty cycle, I can expect that it will never become equal to 1 since the duty cycle is set to 0. But it will keep counting up to 255 and then wrapping around. So, the wrap pulse will keep going up once in every 256 clock cycles. And finally, we have one more register at address number 12, which is 0x0c in hexadecimal. And by the way, it is sort of common convention that we always use hexadecimal for denoting addresses. You have seen this in C for pointers, in embedded C for address registers and so on. And it is just because we know that these multiples of 4, it is more convenient and easier to sort of denote addresses when we write it in hexadecimal, right. So, this is once again a status register which is read only, but also has a behavior where you can do W1C. What does that mean? First thing, it is a status register which is read only. If I read it, then I will find that bit 0 is a wrap bit, which indicates that wraparound has occurred. It is also a sticky bit, which means that even though the wrap pulse which happens inside my PWM core goes high only for a single clock cycle, this will hold that value of wrap, it will become 1 and will stay at 1 until I explicitly clear it. Okay. It also has one more bit which indicates that there is an update pending. We will get to that in a moment, right. What exactly does update pending mean? Well, in short, what it means is, I do not want to change the value of period and duty cycle while in the middle of counting. So, in other words, let us say that my current period was 1000 and the current value of my count, in other words, my system is enabled, it is counting, and the current value of count is, let us say, 250. If I suddenly change the period to 100, this can actually be very confusing. What was I supposed to do? Should I immediately sort of set the wrap flag and go back to 0, or should I continue counting until 1000 and then go back to 0 and next time count only up to 100, or should I do something else? In this case, what we do is we say that if you are in the middle of counting, you will have to wait. Let the system get all the way up to 1000, set the wrap pulse. At that point, any updates that are pending, in other words you want to change the value of the period or the duty cycle, will get updated, right. And this actually introduces, the reason for doing this, which looks complicated, is because it allows us to bring in this nice concept of what are called shadow registers. The idea of a shadow register is, I do not want to change the behavior of a system midway through whatever functionality it is doing. I would rather wait until it gets into some kind of an idle state and then update it. And the simplest way to do that is, I use one extra bit. Whenever enable is equal to 1 and it is counting, I just set update pending, and then as soon as it hits the wrap, in other words when the wrap pulse comes, I say okay, now I have gone back to 0, this is a good time to change my parameters. Take the shadow registers, the period and the duty cycle, and update them to be active values, right. And this is a very common sort of usage scenario. What you can do is, you have some kind of functionality which is long running, you do not want to change its behavior midway through that long running functionality. So, you wait, you copy the values that you want to update into some kind of shadow registers, wait until the present task gets done, update the values, and the next time around you will use the new values, right. So, when you read from this address location 0x0c, you will get two bits, bit 0 and bit 1, which indicate whether a wrap has occurred and whether there is an update pending. The interesting thing is this, so the update pending will automatically get cleared as soon as I wrap around, right, because what it says is, okay, you have finished, you have got up to the wrap, which means your counter has gone back to 0, you can copy the values of period active, period shadow into period active and so on, which means that you can clear this bit of update pending. Wrap on the other hand is a sticky bit. What it says is, once I get a wrap pulse, even if I get another wrap pulse, it does not matter, the bit is going to remain as 1, which is a little confusing. Then what should I do? How do I sort of tell it, okay fine, I know that you have finished wrapping around, now go back to 0. We put that under software control. And what we say is, the easiest way to do this is, you can write 1 to clear. And what that means is, you can basically write 1 into this register, it will clear the wrap bit, it will set it back to 0. If the enable is 1, then of course the next time that it hits the value of wrap, the period, once again wrap will become 1, the sticky wrap status will also become equal to 1, but until that time, the fact that you explicitly cleared it by writing 1 into this register will allow the wrap signal to go back to the value 0.